हाँ जी वो आज बिस्मिल्लाहिर्रहमानिर्रहीम। एम आई जी, पहले मैं पूछ लूं कि एम आई ऑडिबल, मुझे मेरी आवाज आ रही है डॉक्टर साहब?
Ajit, I said you're audible, perfectly fine.
थैंक यू जी, थैंक यू। Bismillahirrahmanirrahim. In the name of Allah, the most gracious and the most merciful. Ladies and gentlemen, Assalamu alaikum and good afternoon from Pakistan Society of Civil Engineers. We are broadcasting this webinar from Lahore, Pakistan. We warmly welcome all participants, including those joining us on Facebook. This is lecture number 71, part of our monthly series that has been ongoing since 2020. Through these series of lectures, PSC aims to provide both young and experienced engineers with the latest knowledge across various civil engineering disciplines. Before I introduce the guest to you and the topic, it's my duty to spell out the rules of this webinar as required by Pakistan Engineering Council. Registered participants for CPT points have to appear live on webcam. However, for ladies, there is an exception. If they wish, they can cover their face while appearing live on webcam. During the lecture, microphone of all the participants except that of speaker shall remain in mute position. As you know, at the last of the lecture, we have 20 minutes of a question answer session. There is a slight change in it today. The speaker will announce during the course of his lecture a 10 minutes question answer session. And during that time, you can type the questions in your chat box and I will read those questions for the speaker to answer. But during the course of the lecture, you can still type in the questions and I will note them down. And when the speaker permits, I will ask him the questions. The second session of question answer of 10 minutes duration will take place at the end of the lecture. So this is how the question answer session will go on today. Participants on Facebook also have the same option. They can type their questions in the chat box and inshallah, I will read them. So today's topic is load and integrity testing of piles, and our guest speaker is Dr. Muhammad Irfan. Dr. Irfan completed his undergraduate and master's degree in civil engineering from UET Lahore in 2008 and 2011 respectively. He then pursued a PhD in geotechnical engineering at the prestigious University of Tokyo, Japan. Dr. Irfan is a highly skilled geotechnical engineer with expertise in foundation design and optimization, shoring systems, and tunnel design. He has extensive experience in geotechnical investigations with a strong focus on slope stability and landslide early warning systems. Dr. Irfan is also a proficient in utilizing finite element modeling to solve complex geotechnical problems, ensuring safety and efficiency in challenging environments. His comprehensive knowledge and practical approach make him a valuable asset in addressing critical geotechnical challenges. With 19 publications to his name, Dr. Irfan has gained 16 years of professional experience in the field. Currently, he is a founder and head of his own consulting firm in Pakistan, where he provides expert geotechnical solutions to various projects. His academic and professional journey reflects his deep commitment to advancing geotechnical engineering. His professional affiliations are with Pakistan Engineering Council, Japanese Geotechnical Society, International Society of Soil Mechanics and Geotechnical Engineering, Japanese Society of Civil Engineers, and Pakistan Geotechnical Engineering Society. I'm now inviting Dr. Muhammad Irfan to please take the floor. Thank you.
Thank you very much, Taisa, for the kind introduction. And I've got an uphill task with me today because I have, when I selected the topic, I wanted to keep it broad so that it gives me a flexibility to tailor things in the end. Like I can probably make it a bit more specific. But what has happened is that by the end, I decided to cover a bit of everything. And because I thought all of these things which I am going to discuss, almost all of them, I see them being used extensively in the Pakistani construction market. And so I thought it's worthwhile using this opportunity and using this platform provided by PSCE to disseminate some knowledge about all of these things. So I have got, so I'll try not to be, I'll try to be specific, providing a general overview of these techniques, what we'll talk about. And I'll try to be more on the practical side, but in order to understand those practical things, there are certain fundamentals that need to be established. So I'll also try to cover those during my talk today. So uh, diving straight into it, the load and integrity testing of the piles. We all know that piles are an important structural component. They find their application in all kinds of structures, from marine and harbors to roads and bridges, and from buildings and storage tanks. So there are all kinds of different applications that we find piles to be used in. Now, there are different kinds of piles that are used worldwide, but in Pakistan, the most common and predominant type of piles which are used are the board piles. And the pile construction, and particularly the construction of board piles, is a very tricky subject, and it's a tricky subject worldwide, not only in Pakistan. Now, why piles? What makes piles as a tricky subject is basically because they are mostly hidden underground. And what I mean by being hidden underground is that you can see a picture here, and you can make your guess what has happened. Why this strange kind of thing? What is that strange kind of thing that is just lifting the car up? You can think of different possibilities of what would have happened. Maybe the driver would have parked the car in the wrong way and just put it somewhere up. But what actually happened was that there was a pile which was being driven on the opposite side of the road. So this is a driven pile which is being driven on the opposite side of the road. And that pile actually bent underneath the ground and actually lifted the car in the parking lot on the opposite side of the road. So this is what I mean when I say that it's a tricky subject, and there are a lot of, because of it being much being hidden underground. And another important thing which makes it critical is that the damages of the piles, if you have any defects, they are rarely repairable. There are obviously ways by which it can be repaired, but they're excessively costly. So you can see all these kind of defects. There is a board pile having a cavity somehow over here. You can get an idea of the scale of the cavity by the people standing around it. You can just think about it now, what can be done to rectify this damage. Now, what has happened here is that there was a board pile, and since this defect, which was identified by some of the techniques that we are going to discuss later in this lecture, because it was identified and the defect was identified to be at a shallow depth, there was excavation done in the nearby areas, and this is why this is visible to us. But imagine if this kind of a defect was deep into the ground. Obviously, you cannot excavate deep into the ground, and that's not going to be a workable solution. And this is all what makes it very, very tricky. Now, it means that because of all these complexities, file quality determination is important. It is of utmost importance to determine the quality of the file. Now, the question is, what do we mean by file quality? What if we want to check the file quality, what we need to check? And the second question is how to check that. So that's the critical part that we need to know. So talking about what needs to be checked, there are basically two things that we can say that needs to be checked. One is the integrity of the file, and second is the load carrying capacity of the file. So these are the two critical or the main things that when we talk about the file quality, these are the two things that we are generally concerned with. Now, how to check those? There are obviously many different techniques, many different methods which are available worldwide to check the integrity of the files. But I'm just going to focus on the techniques which are generally used in Pakistan, mostly used in Pakistan. So I'm just going to focus on those. And these are the three things which we are going to discuss. So basically, I'm going to discuss about the cross-hole sonic logging. Parallel seismic testing, it's not used in Pakistan, but it finds its very interesting application worldwide. And for this reason, I'll provide a brief introduction about it as well. And then the low strain integrity testing, which is commonly known as the sonic integrity testing or the SIT. That's another topic that we'll discuss. And then the second question is then how to determine the load carrying capacity, how to check the load carrying capacity. For this, there are two techniques that we'll be discussing. One is the static file load test, and the other is the high strain dynamic file load test. Now, static file load test, although it's the gold standard, but that's something that I'll just be very briefly touching upon, because I believe even in my last year's lecture at PSCE, we talked a bit about the static file load test, and I think I thought that I should use this time to disseminate knowledge about something which is more important, and that is high strain dynamic file load test, for which the expertise in the local construction industry probably do not exist much. So my main focus today will be, I'll be spending more time on the cross-hole sonic logging and low strain integrity testing, and then finally the high strain dynamic testing. So as Tahir Saab explained, I'll try to that we have a break after this cross-hole sonic logging session, and we have a break of 5 to 10 minutes, have a few questions. Then I'll try that we can have another break after this low strain integrity section, again 5 to 10 minutes. So if you have anything quick, we can catch it up. And then in the end, obviously, we can have more questions. So first, talking about the file integrity, what do we mean by file integrity? So now talking about the file integrity, there are certain things. When we say file integrity, we are basically interested about the file length, its cross-sectional uniformity, whether it is uniform or not. What I mean by this is, you would remember in your undergrad, whenever you are solving problems dealing with files, you are drawing straight vertical lines to represent a file. But in actuality, this is how the file profile looks like. It's never perfectly straight lines. This is how non-uniform, particularly the board file cross-sections are. So when we talk about integrity, we are interested to know about the cross-sectional uniformity of the file. We're also interested to know if there are any soil inclusions in it. We'll talk more about it later. The quality of the concrete, and if there are any joints or cracks which were there during construction. So that's what we mean by file integrity in general. Then talking about the second thing, the load carrying capacity of the file. But in the load carrying capacity of the file, what we want to see is that what is the maximum load the file can carry before failure. Like, what is the maximum load carrying capacity? This value is somehow similar to the yield strength of steel or the compressive strength of concrete that we use. Although there is a lot of complexity behind it, and I personally do not agree with using the term capacity quite a lot. But still, just to keep things simple, we are going to follow the nomenclature which is commonly acceptable. So this is the brief introduction about those. Now I'll jump straight away and let's talk about what is cross-hole sonic logging and how the cross-hole sonic logging is used to check the integrity of the files. Now, to set some fundamental principles there, let's imagine that we have a concrete dock. and we put two sensors on either sides of this concrete block. We have one sensor, which is a transmitter. So basically what it does is this transmitter is capable of generating mechanical waves. This transmitter is capable of generating pulses or vibrations. What I mean by mechanical waves is something similar by a similar kind of a mechanism by which you are able to hear my voice. Are the sound waves are the mechanical waves, and we all know that when someone is speaking, so there is compression and rarefaction in the air, and because of this movement, this mechanical movement, compression and rarefaction of the air, the sound wave travel through, it transmits to the other person's ear. In the same way, let's imagine we have a transmitter which is capable of producing these kind of mechanical vibrations in the concrete. So when this transmitter transmits those waves are received at the other end by a similar kind of a sensor, which we call as the receiver. So when the transmitter gives a pulse, it is received on the other end, and there is obviously going to be some time taken in the transmission of the wave from the transmitter to the receiver. Let's call it T1. And let's call the velocity of transmission of this wave as V1. Now let's imagine that we have a different scenario, that in this concrete block, there is a cavity in between. Now, if there is a cavity in between, what will happen then? The same transmitter, when it is going to transmit the wave will probably receive the receiver, but it will probably have to take a longer path to reach the receiver. And in order to do so, if we call the time taken by the wave from traveling from the transmitter to the receiver as T2 and the corresponding velocity as V2, so we know that the time taken T2 is going to be larger than T1. And similarly, the velocity in case of a cavity is going to be smaller than the first case. Now, this simple principle that I've shown at the bottom, that the difference in the time travel or the difference in the wave velocity is the basic principle that is used in the cross-hole sonic logging and the other techniques that we are going to talk about. So this slide is of utmost importance for you to understand the fundamental principle based upon which all these techniques operate. So the mechanical waves transmitted from one end by any way reach a receiver at the other end, and it is any defect in the concrete surface changes its velocity, changes its travel time. So that's the fundamental principle that all of you need to know. Now let's extend it a little bit on a pile surface. So let's imagine that we have a pile. So you can see if we put sensors at different locations along the pile on this imaginary pile, we see that the wave velocity in this first case at the top is going to be different compared to this second case, and different in compared to this third case. And in fourth case, if there is a big enough crack, the wave might not even be able to travel to the other end to the receiver and just going to be reflected back. So this shows you some real life scenario of how the same technology or same technique is applied in case of piles. Now let's extend this example into cross-hole sonic logging. Now what happens in case of cross-hole sonic logging? What we do something exactly similar. There is a pile, you install two pipes in the pile, as you can see in this image. So these two piles are installed in the pile while during casting. So these pipes are installed, and then some sensors are lowered inside these two pipes. So one of these sensors is called a transmitter, and the other sensor is called the receiver. Now, as you are pulling these sensors up, any defect that comes in its way, the change in the wave velocity or the change in the travel time is something which is going to give us an indication not only of the defect, but by using advanced signal processing techniques, one can determine and get an idea about the size and the location and the type of the defect. That's also possible. So These sensors are pulled together upward and then ultimately connected to a computer. So that's what you call as the cross-hole sonic logging. Now, to get a better idea again about this, let's see how the waves propagate in case of a pile. Let's imagine we have a pile which has two tubes, one tube over here, the second tube on the other end. This one tube, there is a transmitter over here, and the other tube on the right side has a receiver. So when the transmitter starts transmitting the signal at the start of the time, as you can see here, so this signal starts propagating in all directions. This signal does not only start propagating towards the receiver, but it also propagates in the opposite direction. And you can see that there are reflections from the signal striking with the pile boundary that is also now coming towards start traveling towards the receiver. So basically, this wavefront is the initial wave or the actual wave which is moving. And then there are a lot of other reflections which are following this. And if we extend it further, we can see that once the first signal is received here, besides it, there are a number of other signals which are also coming over here. Now, what we can do is that when we started the transmission and when we received the signal, if we start noting the if we start plotting the signal on a time axis, so we call it the x-axis as the time axis, and this is the magnitude of the signal on the y-axis. So we can notice that this is the first arrival of the signal, as you can see here. But if this was the first arrival of the signal, then the thing is why there are more vibrations afterward? Because there are more signals which are coming by falling it. So that's the reason you get a response of this sort. Now, let me simplify it. I'm going to move on the next slide. I'm going to make a simplified figure of the same signal. Now, this is a simplified figure of the same signal. This was the initial emitted signal, the transmission, the pulse that we gave in. And let's imagine that this is the received signal that we started receiving, the one which I showed on the previous slide. Now, how the cross-hole sonic logging actually represents this data? Cross-hole sonic logging actually represents this data in the form of this kind of an image, which is known as a waterfall diagram. Now, this is the waterfall diagram that a typical output of a cross-hole sonic logging shows. You can see the y-axis. You can see the y-axis is the length or the depth of the pile, and so this is the signal along the depth of the pile. So what are this? The signal that we received was of this sort. What are these black and white things that we can see here? In order to understand this, what we do is, since we put the sensors at the bottom, and we started pulling them upward, and there was a repeated signal that we were getting, and we were getting so many of such signals at a very small interval of time. So it would not be possible to plot all these signals along the depth. So a simplified way of doing it is that we take the positive values as black and the negative values as white color and show them depth-wise. So this is what we call as the waterfall diagram. This is the basic waterfall diagram that we see. So in order to understand it better, we have a pile, and in this pile, we install two tubes during construction, and then we fill these tubes with water, which is a requirement. And then these are the probes which we insert in these pipes. Then we gradually pull those probes upward. And as we gradually pull those probes upward, we get this waterfall diagram, as I explained in the previous slide. And in reality, these are not the two tubes that I said. There are multiple tubes that are to be installed. I'll explain on the next slide how many are required, but there are multiple tubes which are installed, and the signal is received between each set of two tubes. So this is how it is done practically. Then there are ASTM recommendations regarding how many number of tubes you are to use. So if for a pile diameter of less than 1000 mm, you can use up to 3 tubes. But if you pile dia exceeds 1000 mm, the number of tubes that needs to be used are 4. And you can see what happens is that if the pile dia is up to 1000 mm, what is going to happen? So we are going to just see the response or the behavior of the concrete in along these 3 lines. It is not possible to get an idea of how the quality of the concrete is outside these profiles. So this is the limitation of this test. For the same reason, as the diameter increases, the code suggests to increase the number of probes, as you can see here. So you can see there were 3 profiles that we were making: profile 1, 2, profile 2, 3, and profile 3, 1. But if we are using 4 probes, all of a sudden the number of profiles has increased from 3 to 6. So there are 2 more profiles in between. And similarly, if the pile dia increases further beyond 1400 mm, the code suggests to go for 6 probes, and 6 probe means it's like 15 profiles that you're going to make. And this is just a demonstration of a cross-hole sonic logging test being done practically at site. This is how it is done. Now the thing is, okay, we have got this waterfall diagram, we have got these output results. Now how to analyze the data, what to look in this, how do we proceed further? So basically there are 2 things that we need to look at. One is we call as the first arrival time, or which is commonly called as FAT, and the second is the signal energy or the amplitude. Now you remember, this is how the actual signal looks like. What we have done is we have taken the positive side and give it a color, say green here, and we have taken the negative side, the amplitude of the negative side, and given it a white color. This is how we reach this waterfall diagram. Now, if we want to see the first arrival time and the signal amplitude, so this signal is processed further, and you can see that we have the first arrival time plotted here. Same thing extrapolated from the same graph. From the watershed diagram, we have extrapolated it here. And also the energy of the signal means what was the magnitude of the signal on the positive side and what was the magnitude of the signal on the negative side. That is what we mean by the energy, and that's also plotted here. So once you are to analyze the CSL data, you have to look at the FAT and the signal energy. So these are the 2 things that one need to look at. Okay, so now we know about the FAT and the energy. The next question is how to find these defects. So in order to find defects, you can then again see the change in the FAT or change in the energy to determine the defects. For example, in this watershed diagram, you can just clearly get an idea that where the consistency of the colors is fine, this is a good part of the profile, and where there is a white part, this is where you have a possible defect. Same is the case at the bottom, and the extrapolated FAT lines and the energy lines also show you the same picture. Giving you more examples of this thing, this is another watershed diagram. And in this watershed diagram, you can see that if you look at this depth, say up to around 25 feet depth, so where there is no apparent anomaly in the pile, the response would look something like this. And in the defected part, the response would look something like this. So what are the 2 differences? The first difference is that there is a delayed first arrival time. So this was the first arrival time. Remember, x-axis is the time axis. So this was the first arrival time for the good response. And this was the first arrival time for the defected part. So basically, there is a time lag which is there. So FAT has reduced basically because of the defect. And in the same way, the energy has also reduced. You can see the amplitude of the signal, of the good signal, and amplitude of the defected signal is very different. And the defected signal indicates that, so the weak amplitude of the received defected signal indicates that there is a defect. And in fact, what was interesting was that in this file, they did coring in the file center. And once they did coring, they found out that at this defected part, this was the condition of concrete. Rather, there was no concrete. You can see that it's pretty much like aggregate over there. So let's see. Uh, let's see some other critical things. The first question is when to test. So when we need to test. So you have casted the pile today. What is the right time to do the test? Now, in this case, ASTM suggests that you should not test before 3 to 7 days after casting. And if you look at the French standard or some other European standards, they suggest a minimum of 7 days wait. And why this is so is because in these 4 waterfall diagrams that you see here, these are the waterfall diagrams of the same pile tested at different days. So this was the same pile under same conditions tested on day number 1. And you can see it seems that there is a defect over here. But on day 2, it seems that the defect is gone or it has healed somehow. And gradually, as you move to day number 4, the concrete has gained strength. The soil surrounding the pile has uh, has came to equilibrium probably. The excess pore water pressures would have dissipated, and now is probably the right time to test. In the same way, another example is that this is the waterfall diagram of a pile which was tested after 10 days. And you can possibly clearly see our defect here. But the same pile, when tested after 13 days, you can see that there is less likelihood of a crack. Yes, you can still feel some problem, but it's not as evident over there. So basically, you should let the concrete gain its strength, number 1. And also, depending upon the soil strata there, how much time it needs to reach equilibrium is probably the right time to test. Now, let's see some practical examples of anomalies. So what the waterfall diagrams, the first arrival time, and the energy look like when you have a top anomaly. So if you have an anomaly somewhere close to the top part of the pile, so this is how the watershed diagram looks like. You can clearly see the white part here in all profiles. So in all profiles, you can see that there is a defect at the same depth. And they did some coring again in this pile. And from the coring, they found out that at the defect location, the concrete was clearly segregated and had a very poor quality. Then this is another example of a top anomaly, a similar kind of an example where you'd see the watershed diagram clearly indicating white part. Again, you see the concrete quality right from the text here, you can get an idea that the concrete quality is quite poor. And as you bypass this section, you can all of a sudden see a much better concrete here in the right part. Then similarly, if you have a bottom anomaly at near the bottom of the pile, so how does it look like? This was identified by CSL, and then they did some coring and they found that there was minimal or absolutely no recovery in this part. So it was pretty much like a washed toe. It was a soft toe condition and having absolutely or no concrete at the toe. Another example of bottom anomaly is here, where you can see in the top part, it seems all clear. And in the bottom part, you can see there is a possibility of some anomaly. These are the reflectograms or the watershed diagrams along the perimeters. And these are for the major diagonals and for the minor diagonals. So in the top part of the pile, where there seemed to be no defect, you can see a very good quality core was recovered. And when you look at the bottom part, in the bottom part, there was this was the condition of the concrete. It seems like in a very poor condition. And in fact, this was so bad that you can just hold it in your hand, it will get converted into sand. So this, again, is identified as a major defect. Similarly, we can see an example of a mid-shaft anomaly. So over here, we can find that there is possibly an anomaly from 28 feet to around 40 feet. Again, a core was extracted, and in this core, you can see that there was solid core down to 28 feet, and after that, it was clean sand. There was no, pretty much no concrete core that was recovered. Another interesting thing that you can figure out was that if we look at all these profiles, so there were 4 tubes, 1, 2, 3, 4. If you look at all these profiles, and you'd see that all these defects are more prominent wherever you have a number 2. So close to pipe number 2, you can see that there is a more bigger chance. So this one does not have number 2. So there is a less of a appearance of an anomaly here. Same is the case here. So this gives you an idea that possibly there was a small flaw which was in the vicinity of tube number 2. So this is how you can actually use this thing to get some idea about the location of the anomaly. And the same technique is actually used in 3D tomography of the CSL of cross-sonic logging as well. Now, finally, you have got the CSL, you have performed the test. Now, how to do interpretation? In order to do interpretation, it's a very tricky thing once again, because there were no clear standards or guidelines that existed. And then back in 2019, October 2019, there was a 3 years research done by all the authorities on the topic in the world, and it was sponsored and managed by DFI, the Deep Foundations Institute of USA, and they came up with certain recommendations, which I'm just going to try and explain here. So this graph actually summarizes what they presented. They presented that, so before we go there, we know 2 things. One is that if you have a defect, the energy of the signal reduces. And second, that the first arrival time also increases. So they categorize the piles based upon these 2 things. And they mentioned that if the first arrival time increase in the fat is more than 15%, and the reduction in the energy is more than 9 decibels, the pile lies in category B. So if the pile lies in category B, how to deal with that pile? So these are the guidelines which they proposed for that. I'll not go in a lot into its detail because I've mentioned the reference, you can go through it. But important thing is, you should always consider the depth and location and the number of the affected profile. They clearly mention that it's a location or a profile which you categorize as A, B, or C. You do not categorize the whole pile as category B or C or A. So one class B result at mid depth does not make the entire pile shaft as class B. You have to use your engineering judgment, and based upon your engineering judgment, the designer have to then make a decision accordingly. And in the same way, if the pile lies in category C, then the first 4 things that one has to see are the same. And then the next steps are that if the anomaly is near the ground surface, you have to excavate, you can core drill, and then maybe some other tests like the high strain test or any other test that may be required for that case. Another critical issue that often comes up in cross-hole sonic logging is debonding. Now, what do we mean by debonding is that the tubes that we put in the pipe, they have to be firmly in contact with the concrete and then filled with water so that there is no cavity around. Because if there is any cavity, if those pipes are debonded from the surrounding concrete, it means that there is a gap, and because of that gap, the wave cannot travel. Now, for this reason, the ASM standard and other codes, they prefer using concrete, they prefer using steel pipes always. The reason is that the coefficient of thermal expansion of concrete and steel is pretty similar, but they do not disallow the use of PVC. But you should remember that if you use PVC pipes, there is always a chance of debonding, but uh, but this debonding has been experimentally found out that this is mostly near the top of the pile. Now, if it is near the top of the pile, what you can do, you can flood the shaft top. If you see these kind of results, you can flood the pile top with water, leave it for some time in the same way. All the cavities are going to be filled with water, and then the wave can propagate. For example, this was before flooding, and this was the waterfall diagram after flooding. So that's another important thing that one has to consider. And sometimes we create our own problems. For example, sometimes in the pile, there is so much reinforcement, which might be structurally required. But these reinforcements are, one has to appreciate that these reinforcements are going to interfere with the waves. And your results are probably not going to be as per your expectation. And again, sometimes we do blunders. For example, like this, that CSL pipes are installed outside the casing, as is the case here or here. So if they are outside the casing, obviously there's going to be interference between the waves with the steel reinforcement. And then finally, a very quick overview of the tomography. As I explained earlier, if you have local defects, there are techniques available by which you can actually make 3D models of those defects. So sometimes, if it's a big pile and there are some small defects which are observed, so instead of outrightly rejecting that pile, or instead of right away going for PDA or high strain dynamic testing kind of testing, which might be more expensive, a cheaper first step can be that you can go for a 3D tomography. And that 3D tomography can create a 3D image, and it can give you some idea about the extent of the damage. The extent of the damage is something that you're going to get. But then the other problem that comes up, and that other problem is, which I'll actually explain more when I will go to sonic integrity testing, is that when you identify these defects, so in the local construction industry, you'd have one as a pile testing agency and other as the designer. Now, the pile testing agency, its responsibility and its capabilities are to test the pile and give you their understanding and interpretation of the possible defect. But it is not in their domain whether to accept or reject the pile. That is the decision that the designer has to take, because designer is the one who has the complete picture in front of them. They are the ones who has an idea of what are the loads which are coming on the pile, what are the different loading conditions, how the load redistribution can be done, what is the location of this defect, and can this defect location, a defect of this size at this location, can it be ignored or not? So all these factors need to be considered by the designers while taking the decision. I'll talk more about it when we talk for the low strain integrity testing. And then very quickly, the parallel seismic testing. Now, we talked about cross-hole sonic logging, but there are cases many times when you have piles with something already constructed at the top, and you have absolutely no idea of what type of pile is this, what is the depth of the pile, and you have absolutely no idea. So in order to, if you have structures which are already built on top of the piles and you are interested to know what lies underneath, this technique of parallel seismic testing is something which can be used over there. Now, in parallel seismic testing, what you do is you install a pipe, you actually drill a borehole as close to the pile as possible. And this borehole has to extend at least 15 feet below the expected pile tip. So you drill a borehole adjacent to the pile, you insert a sensor in it, and then you apply impacts at the top of the pile. So what happens is that when this wave travels from the pile and then through the soil to the sensor, like is signal A or this signal B, the time taken by the wave in traveling from on path A and path B and path C is quite different. Because what happens is if you plot all these signals along the depth, you would see a clear difference in the slope of the first arrival time. And that change in slope is what gives you an idea about the pile toe. So this is how this can be used. This cross-hole sonic logging, this parallel seismic testing can be used for determining the unknown lengths of the piles with a structure built at the top. And some major limitations of this method are that you need to drill a borehole. It's not so accurate for integrity testing. It does not tell you a very good idea about the pile integrity. And it's highly dependent upon the soil profile, and it's expensive mainly because of drilling the borehole. And I think we should take a quick break here, maybe for 5 to 10 minutes. And Tahir Sahab, if the audience have some question, I would be happy to answer.
Yeah, I have requested the audience to type the questions in the chat box. So far, I can't see any questions typed there. So taking the opportunity of this break, I would like to thank you, Dr. Irshad Ahmed, who has joined us uh, uh, during the course of the lecture. Dr. Irshad Ahmed is the head of the department of UET Peshawar, Civil Engineering Department, UET Peshawar. So thank you very much for joining us, Dr. Irshad Ahmed. And if there are any questions, yeah, I can see somebody has typed something. Amir Yasir, Dr. Irfan, Amir Yasir has text CSL limitations. He's asking about the limitations. And then he has added at how much depth it will give us results.
So there are obviously quite a lot of limitations of CSL as for any other technique. One of them I tried explaining in one of the slides, that since the CSL pipes are generally installed inside the cage, so they can only give you an idea about the quality of the concrete in the path that lies between the two probes, between the two pipes. It cannot effectively look outside it. So if you have something outside the cage, like some necking or something, so CSL would probably not give you any idea about it. And as far as the depth is concerned, there is no limitation of the depth because as deep as you can take your sensor. So probably the only limitation is how much is the length of the cable that you're carrying with your equipment. So there is no other limitation of the depth.
So audience, kindly, if anybody has any question, kindly type it. Otherwise, we will proceed with the low strain integrity testing. The next subtopic. So Dr. Irshad Saab, thank you again for joining. And at the end of the lecture, I would like you to say a few words about the lecture and about the society. Thank you. At the end of the lecture, I'll give you the opportunity. Thank you, sir.
So Taisab, I think we should continue.
I think we should continue. If there is no question, if a question comes, then we will take it in the next session or the last. Thank you.
Yeah, that's good. Thank you.
Carry on.
Okay, so let's move to the low strain integrity testing or the sonic integrity testing. Again, the basic working principle is similar to what we have discussed earlier. Let's imagine we have a pile. We apply an impact through a small hammer, and this wave travels down the pile, it gets reflected from the bottom of the pile and comes back up, where we have placed a receiver, and that is again an accelerometer in itself. So this, what we do is, again, we are just measuring the travel time of the wave from the pile head to the bottom and then back up. So the important thing to remember is that the travel time that we are measuring is actually twice the length of the pile. So that's a critical point that you need to remember. And this same principle of SIT is something which is going to be used when we are going to move to the dynamic pile testing as well. So let's imagine that we have a crack now in the center of the pile. Now, if there is a crack, what will happen? If you again apply an impact, this will come down, it will get reflected back from the receiver. So the travel time which you will have in this case is now going to be, in fact, I need to just swap it a little bit. So the travel time is going to, T2 is going to be less than T1. And similarly, the velocity is going to be affected in the same way. Now, talking about this, so in the same way, so this is how the typical reflectogram looks like. You have a transmitted signal. This is the transmitted signal. And this is the received signal in case of T2. So this was the shorter signal which reflected from the crack. So this is the travel time in this case. And then if we look at the actual travel time for the whole pile, it will be like this. So what I was discussing, that the change in the travel time is something which gives us an idea about the distance traveled by the wave. So this is the same thing which we use in case of for data interpretation. The travel time between the impacts and the return signal gives the pile length. So we need to remember that the time travel is actually twice the length, because as I explained previously, the wave has traveled down the pile to the bottom and then came back up. And if we assume the wave speed as a typical wave speed in concrete, we can actually determine the length of the pile and also determine the possible anomalies or the defects. Now, what are the various applications of this? There are different kinds of defects in the piles which we can identify. We can evaluate the cross sections and the lengths. We can get some idea in some cases about the unknown length as well. We can get an idea about the continuity of the pile. For example, if there is a major defect, so the continuity of the pile is going to be affected, and we can get an idea of that by using SIT. And we can also get an idea about the consistency of the pile. For example, if there are some soil inclusions in the pile during construction, we can get an idea of that from SIT. So let's see some practical examples of this. But before that, how to actually perform this test carefully, some key things that I see need to be understood. First, you need to prepare the pile head. And that is something which is taken very lightly in the professional practice I've seen, but this is something which is of utmost importance. Why I say so is that now you know that the wave is going to travel down and then going to come up and is going to be picked up by this receiver. So this receiver, if it is not properly in contact with the pile, it is not going to receive a good wave. And even a good quality pile might start appearing to have some defects just because of a poorly prepared pile head. So pile head preparation is very important. That is something that needs to be considered. Then another important thing is that there has to be a minimum distance. ASTM recommends minimum of 300 mm between the pile and the impact. And lastly, you should not put your sensor close to the edge, because if it's close to the edge, there are quite a lot of interferences from the boundary effects, which are going to affect your signal. So that's, again, going to impact your results. And there is just one basic equation which controls or defines the SIT response. And this equation goes like this, where Z is the impedance, A is the cross-sectional area, E is the modulus of elasticity of the material through which the wave is propagating, and rho is the density. Now, what happens is that any change in either of these, either the cross-sectional area, the modulus of elasticity, or the density, is going to make a change in the impedance. And it is the change in the impedance which actually makes the signal change its shape. So, for example, you put an impact at the top, the wave, which was initially like this, it started traveling to the bottom. And what happened at the bottom? At the bottom, so while the wave was traveling through the pile, the cross-sectional area was the same, the modulus of elasticity of the pile material was the same, and the density was the same. But when the wave reached the bottom, what has happened? When the wave reached the bottom, actually the cross-sectional area has changed because there's a sudden reduction. Then the modulus of elasticity of the wave, which was initially traveling from concrete, now it has to start traveling into a different medium, which is soil underneath. So it means the modulus of elasticity and the density has also changed. So it means that there is a change in the impedance, and that change in the impedance is something that actually makes the reflection come back up and appear as a reverse signal. And this is the same concept which is going to be used everywhere in SIT and also in the high strain dynamic testing. For example, just to explain it a little bit more, let's assume a pile which of a uniform cross-sectional area, and then there is a reduction in the cross-sectional area at the bottom. Now, if there is a reduction in the cross-sectional area, what's going to happen? So the cross-sectional area, E and rho are the same down till this point. But beyond this point, there is a change in the cross-sectional area. E and rho are the same. But because there is a change in the cross-sectional area, so a wave is going to be reflected back from here, and it's going to appear as a signal, as a reflected signal in your reflectogram. And similarly, the other reflection is going to come when this wave is going to reach the bottom. And from this bottom, when it's going to come up, you're going to see another reflection. So you see, this defect or this change in cross-sectional area appears as a change in the impedance. And this is what we see in the reflectogram. And these are just some typical summary of how the reflectograms look like for different types of piles. So you have, if you have a straight pile which has a free end at the bottom, so this is the typical reflectogram that you would see. This is something similar to what I have explained on the previous slide. But if the pile bottom is fixed, what I mean by that is that if the pile bottom, for example, if a pile is rock socketed and if it has a fixed bottom, there is a reversal in stresses at the toe, and because of the reversal in stresses, the polarity of the signal changes. So previously it was downward, and for a fixed-ended pile, it flips upward. And this is a reflectogram for a pile which is shorter than normal. Then if you have an increase in cross-sectional area, so increase in cross-sectional area, think back of the equation that we saw on the previous slide. Increase in cross-sectional area will increase the impedance. And this is what you see. You can see an increase in the impedance here. And then finally, the decrease in the cross-sectional area at the toe is what you see, a decrease in the cross-sectional area at the toe over here. Similarly, if the pile cross-sectional area is reduced, you would find the decrease in the impedance represented in the reflectogram, and same is the case in the toe. So in the same way, you can, if you understand these basics, you can start understanding the SIT signals, how they work. So if you have a good pile without any defects, so this is how the typical reflectogram looks like for a free end pile. Like if you do in alluvium, this is how the typical reflectogram would look like. And if we take a fixed end pile or a rock socketed pile resting on a bedrock, for example, so the reflectogram looks similar. The only difference is that the polarity changes to positive. Now, if you have a damage in the pile, so you can see this is the pile toe somewhere over here, and this damage appears as an impedance reduction earlier somewhere in the reflectogram. Now, what would you have if there is a crack or a defect there? So you applied an impact, the wave started traveling down, and then from this crack, the wave will reflect backward up. Again, when the wave reaches the top, the wave automatically is reflected back to the crack. So this is important to understand. You see, you provide one impact, the wave goes down, it goes back up, and then it starts come back and it starts moving up and down in this zone. This is what you would see. And how it comes in reality is something of this sort. In this case, what you would see is that if there is a defect at the top, so because of this defect at the top, you see all these vibrations coming, and the actual toe cannot be seen because the major signal was just being reflected in this zone, and it could not go to the bottom. So that's the scenario. Now, soil strata plays a big role in understanding and interpreting SIT reflection. What I mean by that is, so let's imagine a precast pile which was tested before driving. So this is a precast pile. Remember, this is not a board pile I'm talking about. This is a precast pile. So if it's a precast pile, it has a very uniform cross-sectional area. Now we are going to drive this pile into the ground, something similar to what we do as we drive a nail into a wall. In the same way, we drive these piles into the ground. So if it is a precast pile, before driving, this is the reflectogram. And once you do driving, this is how the reflectogram of the same pile without any defect looks like. Now you can see that all these changes are basically the reflections from the soil. So if all these reflections are basically from the soil, it means for good interpretation of sonic integrity test results, it is not possible to do good interpretation without the soil boring results. You need to have a very good geotechnical information. You have to have a very good pile construction record to give any final verdict about the possible defects, because there are lots of changes in the impedance that you would see, which are mainly because of the reflection from the soil. Now, in these two reflectograms that we have seen, there is another thing that is important. What is the other thing that you notice besides only the shape changing? There is another thing which is changing significantly. And that is that if you notice the magnitude of the received signal, the magnitude of the signal which was received from the toe, it's significantly larger when the pile was outside the ground, and it diminishes very significantly when you actually drive it into the ground. Now, what has happened here is that because of all these impedance changes, all these reflections from the soil, the signal is being attenuated. The signal is being dampened. So the signal keeps on losing its energy. And because the signal keeps on losing its energy, because of that reason, the amplitude of the received signal also decreases. Now, if the amplitude of the received signal decreases, there is a simple solution what we can do, and that is that we can amplify this signal. So we can amplify the entire signal, and that is something that I'm going to explain on the next slide. So you have understood what is the necessity of amplification. Now let's see some more details about this amplification. Now this is a signal before amplification. You can see you cannot, or you can barely see where the toe is. But if we amplify the same signal, we can start seeing the toe. But it is not only the toe that we have started seeing, we also start seeing the other reflections which were before. And the other important thing to notice is that this attenuation of the signal, or this damping of the signal as the signal is going down and it's coming up, this change or loss in amplitude follows a logarithmic pattern. This follows a logarithmic pattern. So for that reason, the amplification that you apply has to follow a logarithmic path, logarithmic manner as well. And what I mean, if we follow a logarithmic manner, the simple check for that is in your SIT software, when you are actually amplifying, good amplification means that the response of from your toe should have a similar magnitude as your initial signal. If you have amplified it too much, it means if the amplitude here is more than the input signal, it means you have amplified it too much. And if it is smaller than the input signal, it means you have amplified less than what was required. When there is signal smoothing, there are often quite a lot of reflections from the top, and because of these reflections, the toe is not visible clearly. As you can see, we cannot see the toe signal. So if the toe signal is not visible, you apply some filters, some high pass or the low pass filters to make the signal smooth. So that is something which is done very commonly. Everyone has to do it. Everyone does it. But one has to be very clear that that the filter to be used has to be as smaller as possible, because what happens is that a lot of useful information is lost if you are using filters excessively. For example, in this file, there was a defect at the top, but just because we are using a too bigger filter, that information about the defect is lost. And if you are reviewing the report, you would feel that there is no defect here, whereas in reality, there was some defect over here. So one has to be very clear about the filter that one is using, and better yet, to use a similar filter across all the piles at the same site and keep its value to be minimum and have it reported as well. And then finally, what is a characteristic signal? So these are all different signals from different piles taken at a project site. You would see probably all of them look almost the same, except one, which is this one. So if you try noticing that the shape of this signal is somehow different compared to the other signals or the other piles that you have seen. What I mean, what happens is that for a same site having same piles, the shape of the reflectograms should be similar as well. So if the typical shape of the reflectogram is something that we can establish, and that is something we call as the characteristic signal. So what I mean is that if we have established a characteristic signal, as can be shown by red line here, and if we compare any pile with this characteristic signal, we can get an idea whether there is any problem in this pile, or the humps that you would see are only because of the characteristic behavior of that site or the characteristic behavior of that soil. For example, if we plot signal of pile number 38, as was shown on the previous slide, you'd see a clear difference in clear deviation from the characteristic curve, indicating the pile to have an anomaly or a defect there. Then finally, how to accept or reject the piles? What is the criteria for the acceptance or rejection of the piles? There is too much text here. I'm not going to go through the details of this. I just wanted to specify a couple of important things. It is important to remember that there is no standardized criteria that is acceptable worldwide. There are different standards, there are different codes which give their own guidelines. For example, the British code in Syria, they classify the SIT tested piles into 4 categories: class 0, 1, 2, and 3, and onwards. But the reference, which in my opinion holds quite a lot of value, was after quite a lot of research. It was a Transportation Research Board funded work which was published in 2011, and they classified the piles into all these different categories. And based upon these categories, the designers then can have some idea of the quality of the pile pretty quickly. But again, these are all qualitative results, and quantitative assessment is somehow not possible. Rather, more often than not, it's not possible. Now, if you want to do SIT and for the sonic integrity testing, what are the important things that you should consider? First, at any given site, at least 25% of the piles must be tested. because this is the bare minimum number of piles that are to be tested to get some confidence about the characteristics of that site. And since it's quite a cheaper test to conduct and it doesn't cost you much money, so it's always better to do it on 100% of the pile. And that's something which is recommended by many design guidelines as well. And for each pile, I would always suggest to get at least 10 consistent blows and take an average of those, because there is a lot of variation in from one blow to the other. So you want to get the characteristic behavior from each pile. So get at least 10 blows. Use minimum filtering as what we discussed. The amplification should be optimal. We talked about the characteristic signal. And it's also important that you compare your signal with the boring logs wherever possible. It gives you quite a lot of valuable information before deciding whether there is some defect or whether the change in impedance that you observe is mainly because of any soil spreader change. And then finally, and very importantly, in my opinion, that the testing agency should not be expected to give the final verdict, to accept or reject the file. This is the designer's job. And this is an excerpt from the ACM standard of the low-SIN integrity testing as well. And you should get an idea from this as well, that for the piles having minor impedance variation, the engineer should use judgment as to the acceptability of these piles, considering other factors such as the load redistribution to the adjacent piles, load transfer to the soil above, and safety factors and other structural requirements. So that's another important misunderstanding, in my opinion, in our industry that needs to be clarified here. So that was it about the pile integrity testing part. I'll, Taisab, if you think we can, if there are questions, we can have a quick break again for 5 minutes.
Haji, we have questions. So just give me a second. I will read them out. And the first question for this session has come from Kamran Javed, engineer Kamran Javed. He's asking how pile bottom cleaning affects the sonic integrity test, how to deal with it.
So bottom cleaning does affect that. And as I explained in one of the earlier slides, that the textbook shape of the pile that we are used to drawing, in which there are straight vertical lines and a very sharp bottom at the end, it's not the reality most of the times. So, and sometimes if the bottom is not cleaned, the pile bottom, which is not perfectly horizontal, rather it is in a curved shape, that makes it very difficult to get a clear toe reflection. So yes, the bottom cleaning, if it's not there, it even for the same piles, it can give you some indication. But as I mentioned earlier, if you have developed a characteristic curve for the site, that characteristic curve gives you some good idea about about whether the bottom cleaning of any particular pile was the problem or the problem lies somewhere else.
The second question is from Mozam Nawaz. I will read this question very slowly because maybe I really don't know what he's asking. He has written design of pile, that is depth and dia of pile, and its steel reinforcement, vertical and lateral steel bar is the necessity of a project engineer in high-rise buildings, 10-story of 110 feet high. Have pile, then cap and raft. Please share knowledge. Did you understand?
No, to be honest, I think it was not very clear.
Mausam Saab, I will request you to please redraft your question so that we can understand it with clarity, and inshallah, then we will answer it. Now we have another question from Amar Yasir. He's asking again the same question: limitations. How much depth SIT can perform?
Yeah, that's a very interesting and a very relevant question in my opinion.
And let me add his supplementary to this. He's further asking if the pile is bit tilted, does the sonic signals trace the tilt? Thank you.
So I'll share my opinion about the second part first. I think it's an interesting point that you've raised, but I don't think so. Unless it's a better pile which is inclined by a significant margin, I don't think so that this technique has the capability uh, to identify the pile tilt. So I don't think so that's possible. As far as the first part of the question is concerned, regarding the depth up to which the sonic integrity testing can give can get the signal, actually there is no fixed answer for that, and it depends from strata to strata and the pile size to pile size. In general, most of the manufacturers classify the capability of SIT in terms of length to diameter of the pile. And so whatever is the length of the pile, compare it with the diameter of the pile, they typically say that up to a length to diameter ratio of somewhere between 20 to 30 is a reasonable range. But as per my experience, they, it depends if the soil is very high friction soil surrounding the pile. It will probably be very difficult to get a pile toe response even for a very short pile because most of the reflections are taken by the surrounding soil friction. And in some other cases, people have reported testing piles of as long as having a length to diameter ratio of as much as 50 to 60. So if that answers what he was asking.
Now, Mozam Nawaz has redrafted his question and he has just asked a very simple question now. How we can design pile for high-rise building? It is hell of a question. Very, if you can answer it, let's say, please.
Yeah, I think it's beyond the current scope and
Yeah.
beyond
That is what I was trying to say. It is hell of a question involving a lot of things. So, but very design of pile foundation has certain principles, same principles and methods have to be applied here also. But if you want to add anything, Dr. Saab, please add.
So I think it's again the same. Talking about very pile foundation, so high-rise building, one has to see what are the loads which are coming, particularly in case of compression, lateral tension, and all these aspects. And I think, as you just mentioned, all these aspects need to be considered for the design of those foundations.
Yeah, thank you very much. No further questions for this session. Kindly continue with or start the static pile load test. Thank you.
Okay, so let's continue from where we left. So we move to the pile testing. So we are now moving to the second part. We were talking about the pile quality, and we said when we want to observe pile quality, we have to see the integrity of the pile and the load carrying capacity of the pile. So for integrity, we have already seen the different techniques, and now we are moving to the load carrying capacity. And we're going to talk about two things here, the static pile load test and the high strain dynamic pile load test. I'm going to talk very, very briefly about the static pile load test. I talked a bit more in the previous PSCE lecture last year. So, and considering the time constraint, I'll try shedding some light on high strain dynamic pile load test in the coming few minutes. So just a quick overview of what a static pile load test is and what it looks like. What we try doing is we apply a load on the pile. So whatever was the design load that you actually that the actually pile is meant to take during its entire lifespan, you apply a significantly higher portion of that load on the pile, and you apply that load by means of hydraulic jacks, which are placed on top of the pile. And when this hydraulic jack tries opening up, there is a huge reaction in the form of concrete blocks or some other arrangements which you have seen here. So this reaction does not let the hydraulic jack go up, rather have the reaction come down. So this is how you apply the load in case of a static pile load test. And the ultimate goal is to get the load settlement graph, which is something of this sort. And as we have discussed earlier, that from this load settlement graph, what we are actually interested to determine is we are interested to determine the pile capacity and what is the load carrying capacity of the pile. And that load carrying capacity of the pile, as we discussed in the earlier part of the presentation, that is similar to the maximum, that is similar to the yield strength of concrete or the compressive strength of yield strength of steel or the compressive strength of concrete, as is the case. So that's what we are actually looking to do by performing the static pile load test. Now, moving further to the high strain dynamic pile load test. What is the high strain dynamic pile load test? This test method is standardized by the ASTM standard 4945. And if you can just want to get a comparison of the static pile load test versus the high strain dynamic pile load test, you can just get an idea that it would take a long time to make this arrangement compared to this one. And also from the safety viewpoint, it's going to be more challenging compared to the other one. So that's why there was a necessity to come up with a more modern replica of the static pile load test, and which is what the high strain dynamic testing is. And then there are some other cases as well, that there are some locations which are very difficult to perform a static pile load test. For example, in case of offshore piles, it's extremely difficult to perform a static pile load test. So in those cases as well, high strain dynamic testing is something which is quite helpful and is used worldwide. Now, the ultimate goal remains the same. The ultimate goal remains the same, that is to determine the load capacity plot, the load settlement plot. And by using that load settlement plot, we can determine the pile capacity. And the benefit of the high strain dynamic testing is that by using this test, one can easily determine the skin friction and the toe resistance. So you can actually separate these two parts of the pile capacity out. You can separate these two out as the skin friction and the toe resistance. But it's very, very important to mention here is that it's not without bias. What I mean by this is that there is a lot of signal matching and iterative techniques that one has to do. And unless the test is performed with reasonable reliability, and the site information is acquired with reasonable reliability, and then the same data is processed in the same way, it's not without bias. So these values determined by two people can be vastly different. So it is possible that two people analyzing the same pile, one comes up with a pile capacity of, both come up with a pile capacity of 1,000 tons, but their distribution of the skin friction and the toe resistance might be very different. That's possible. So, so the experience of the personnel, it's quite important. And then another benefit is that the mobilized friction along the depth of the pile, mobilized friction along the depth of the pile is something that can also be determined. And again, the same thing is that it's not without bias. Now, how this test is performed? In order to perform this test, the arrangement is such that you have a pile and you install some sensors near the head of the pile. So these are the sensors which are installed near the head of the pile. There is an accelerometer, which is indicated here, and a strain sensor, which is indicated here. And then there is a heavy hammer, which is dropped freely on the pile head. Now, once you drop this hammer on the pile head, there is a wave which is generated. That wave travels down the pile and bounces back up. Now, imagine you can notice that the principle is the same as we have discussed in case of sonic integrity testing. The only difference is that the size of the hammer is much bigger, and the type of one, there are more sensors, and second, the type of the sensors is different in this case, and there are more sensors installed. So when the heavy hammer is dropped on the pile head, a stress wave is generated which travels down and it comes up. And as that stress wave is traveling through the pile, it gathers information about the interaction between the pile and the surrounding soil. And all this information that is gathered, that is stored in the sensor data that you get. So there are two types of data that we get. One we call as the force data, which we obtain from the strain sensors. And second is the particle velocity, which we get from the acceleration sensors over here. In reality, this is how the test looks like. This is the arrangement. There is a guide frame which is provided. There is a hammer in between. The crane lifts this weight up, and then there is a free fall which is applied on the pile head. And this is how these sensors, the accelerometer and the strain sensor, actually looks like. So remember from the previous slide, when we perform the test, we get two types of information. We get the force transmitted to the pile and the force record, and we get the velocity of the particle, the velocity of vibration of the particles, which we get from the accelerometer. So this is how the record looks like. So we have the force record and we have the velocity record. This is a typical output from a high strain dynamic test. This is the raw data that you get most of the times. And again, interesting to note is that this time obviously remains the same. If you remember, I mentioned this travel time of the wave from the pile head to the bottom and then back up is 2L over C. So this remains the same. And this force and the velocity data has actually information about the pile soil interaction. So that is available, stored in it. Now, how this information is stored? What I mean by this, that the force and the velocity data has the soil pile interaction information stored in it. And in order to understand this, let's assume that the soil resistance is like, let's assume the soil resistance somewhere in the middle of the pile. Although it's not like this, but let's assume that there is a point along the pile depth that is the location where soil offers all its resistance. Now, if this is the case, when you apply impact on the top, the wave starts going down. And when the wave reaches here, if you remember the concept that I explained while explaining the sonic integrity testing, as is the case in case of any defect, wherever there is impedance change, and this resistance is an impedance change, because of the change in impedance, there is a reflection that comes back up. And this reflection which comes back up, some part of the wave is coming back up, and the remaining part of the wave goes back down. But this is just for explanation. Let's focus on this force and the velocity graph, what is happening. In very simple words, because of the effect of this resistance, this force and the velocity curve, they start separating out. Previously, by the time where there was no resistance, they were perfectly proportional to each other. They were perfectly overlapping each other. But because of the soil resistance, the force and the velocity, they start separating from each other. Now, this is the key thing which is used in identifying the magnitude of the resistance which is on offer here. Now, just to take it one step ahead, this is the resistance offered at one point. But in reality, this is not the case. The soil is offering resistance at all locations. So what we can do is, if we have, for example, if we again assume 3 resistances like this, or 3 layers from which the resistance is being offered like this, you would have some reflection from the first layer, some reflection from the second layer, and then from the third layer. And what is happening, you can notice that at each subsequent reflection, the force and the velocity curve, their gap opens up more and more and more, indicating that there was less resistance here and more resistance here, and a progressively more resistance in the next part. So that's how the raw data gives you information. Now, now this is an ideal or an assumed case, but how this concept looks like in reality. This is how it looks like in reality. In reality, you can notice that the force curve and the velocity curve, they were proportional till this point, and then they start opening up. And when they started opening up, it means now this is the location where, this is the point from where the soil resistance started offering its effect. So that's why they started opening up, and they started separating out. And then these waves are further processed into wave up, something which we call as the wave up and the wave down curve. These are the, again, important curves which are used in subsequent analysis. If I'll get some time, I'll explain more about it later. But the important thing is that if this difference or this separation between the force up, the force and the velocity curve is something which we call as the soil resistance. Now comes a very interesting and very important point. Now, if it was that simple to determine the soil resistance, then it's very easy. You just look at these graphs, maybe measure their magnitudes. At side, you can tell this is my resistance. But that's not the case. There are so many other phenomena which are taking place in the back end. What I mean to say is that this resistance is called the total resistance of the soil. What I mean to say is this total resistance is not the resistance that I'm interested in. We are actually interested in static resistance of the pile. Now, what is the difference between the static resistance and the total resistance? The total resistance is actually the summation of two components. One is the static resistance, and other is called the dynamic resistance. Our interest is only to determine the static resistance. Now, the question is, what is dynamic resistance and how can we determine that? Now you would probably have never heard about the dynamic capacity or the dynamic resistance of the pile, but in this test, this plays a very important and a very critical role. Now, in order to understand this dynamic resistance, the simplest example is probably to look at this image. So now in this image, someone is expected to get a huge dynamic resistance as he touches the water. So probably from this example, you can get an idea what a dynamic resistance is about. So whenever there is a moving object and it hits a surface, there is a dynamic resistance that they get. The same thing, the exact same phenomena occurs in case of a pile load, in case of a dynamic pile load test as well. What I mean is, when the hammer impacts, because of the impact of the hammer, some of the static friction of the pile activates, but good part of dynamic resistance of the pile is also activated, something similar to a person falling in water. Now, in order to understand it, so in order to elaborate it a little bit more, what I mean by this is, now this dynamic resistance which is offered by the soil, it changes from soil to soil. It is different for gravel and different for all different kinds of soil. What I mean by this is that this, as you can imagine, is a function of the permeability of the soil. If the soil is less pervious, as is the case in case of clays, there is more dynamic resistance, because when the impact applies, there is more pore water pressure which cannot be dissipated very quickly, and because of which there is more dynamic resistance offered to the pile. And on the other hand, if it is a gravelly soil, for example, in that case, there is less dynamic resistance because the pore water pressure can get dissipated very quickly. But the issue is, it is an extremely tricky topic to pick the right dynamic resistance value. So normally what is done is, there are many different approaches, many different methods which are used then to ultimately determine the static pile capacity. One of the methods which is commonly used and which is often the case, which is used at sites as well, if you get an opportunity to observe a dynamic pile load test at site, so most of the time the tester there is talking about the case pile capacity. But the problem that I feel in our industry, that some people, what they do is they they, instead of using the right case damping factor, they only rely on the RMX. So what is RMX? So what the software does is it calculates, or it gives you the capacity for different values of the damping factor. For example, it gives you a pile capacity which is called as RX4, which means it is the case damping, it is the pile capacity by assuming a case damping factor of 0.4. In the same way, there are other pile capacities like RX5, RX6, and so on. Now, the common misconception in our industry is that the RMX value that you get at site, it is equal to the load which was applied at site. It is not the case. That RMX is just one of the maximum possible pile capacities that can be obtained. But it does not mean that that was the actual load that you have applied outside. So that's a misconception that needs to be clarified. And then finally, very quickly, this dynamic pile load test is since you can imagine, it's a larger version of the sonic integrity test, where you just was using a smaller hammer. Here you're using a much bigger hammer, so you can get a very good idea about any damages in the pile, any cracks in the pile, and the parameter that is used is called as the beta factor. And this table just summarizes very quickly that what the beta factor indicates. For a beta factor of less than 0.6 indicates a broken pile. But generally speaking, most of the damages that you see lie in this range of 0.8 to 0.1. So what is important to note is that this dynamic pile load test, it's the only test that we have seen so far in this presentation. That's the only test that gives you information about both things. It tells you about the pile integrity, and it tells you about the pile load carrying capacity. None of the other tests gives you information about both of these things. It either tells you about pile integrity, any of the other tests, or it tells you about the load. So that's the only test which gives you information about both. So just some key points that you need to consider for performing a good dynamic pile load test. First, the hammer should be at least 1 to 2% the weight of the hammer. Some people feel that they can use a lighter hammer, just drop it from a bigger height, and they will get the same response, but it is not the case. When you are if you are increasing the height of the hammer and the weight of the hammer is not appropriate, all you are doing is increasing the dynamic resistance, which is not what is required. We require the static pile capacity, and for that, it is a must that you have 1 to 2% of the load that is to be proven. You need to have the hammer accordingly. What it means is that, for example, if the test load is 1,000 tons, so the weight of the hammer should be between 10 to 20 tons, somewhere in between. And then this is again very important. If during your test for any blow, you get a permanent set of 2 to 3 millimeters, that is what is an indicative that the complete resistance has been mobilized. In most of the cases, we are unable to get this kind of a permanent set, which is an indicative of either the input energy was not enough, or maybe the pile was over-designed. And if the permanent set is very small, or like if on the impact, the settlement of the pile is very small, it means that the results that you have obtained are the lower bound solutions. They are not, the actual capacity of the pile can be much higher. What you have obtained is a lower bound solution only. And other important thing is the sensors that you install should be installed at least 1.5 to 2 diameters below the pile head. However, it's better to use a force transducer at the pile top, which eliminates a lot of the problems commonly associated with the pile heads. And lastly, the drilled shafts, something which we have here, you should at least have 4 strain gauges. This is what ASTM recommends. ASTM recommends to have at least 4 strain gauges and 2 accelerometers for drilled shafts. And always rely on the CAPFAP results. This is the advanced analysis which is finally done. But despite of all these, as I said in the beginning, there are always biases which can be there in this, although a lot of research has been done and it has proven that if done properly, the dynamic pilot test provides you a very good comparison with the static pilot test, but still, static pilot test remains the gold standard worldwide. Thank you very much. That's it for my end. Thank you.
Thank you very much, Dr. Saab. Now we have, before I thank you, there are a few questions we have to. Now, the first one is from Farooq Ahmed. What is the way to get actual value of skin friction in variable strata throughout the depth?
So, what is the way to get?
What is the way? You mean how to calculate the actual value of skin friction in variable strata throughout depth?
So I think if they would have mentioned the method which they are referring to, because as I said earlier, by integrity methods, we cannot get the pile capacity. That's not possible. So probably what I assume is that Mr. Farooq is referring to the high strain dynamic testing, because even in traditional static pile load test, that is also not possible. The traditional static pile load test only gives you the head settlement and nothing else. If you want to get good information about the different layers that can be there in the pile, one, you have to instrument the pile, you have to put sensors along the pile and then perform the pile load test. So that is the gold standard. And if you are talking about the dynamic pile load test, so in case of dynamic pile load test, CAPRAP analysis can do that, but it has to be complemented by very good geotechnical borehole log with it as well.
Farooq Saab has asked another question. Please provide your expert opinion whether we can design working piles based on HSDT data.
So there are two things. In my personal opinion, a good thing to do is you have to divide your testing into two parts, two phases, as is the practice worldwide. One has to be the prototype testing, in which you cast a test pile. The objective of those test piles are to load them till failure, have sensors and instruments installed in them, and get the maximum information out of them. And if you are able to do that, then when you go to the working part of your project, like the working piles, for those working piles, you can definitely perform high strain dynamic testing. I think because the objective there is mainly two. One is to prove whether the load is being carried by the piles which have been casted, and second is to know about the integrity, and that is something which can be done fairly reliably with high strain dynamic testing.
Mr. Farooq has asked another question. Can we use HSDT test pile as a working pile?
Yes, it can be used depending upon how much permanent set was there. Because the ASTM generally suggests that around 2 to 3 millimeter of permanent set is something which is anticipated as a result of a high strain dynamic pile load test. And that is only if there is a full mobilization of the pile capacity, which is generally not the case many a times. So I think it can easily be used as a working pile.
Okay, now Kamran Javed, engineer Kamran Javed has asked, how can HSDT results be correlated with static load test data for foundation capacity assessment?
That can definitely be done, but there are two things about it. There are academic researches that have been done worldwide, and you would find a lot of literature on this by Professor Likens and Roosh and others about this, where they have correlated the static pile load test and the dynamic pile load test, and they found very good comparison between these two. in many cases. And then there is another thing which is for the practical purposes. For the practical purposes, it is possible, it can be done that you have a test file campaign, and in that test file campaign, on the same file, you first subject it to dynamic pilot test, and then you perform the static pilot test. That gives you an added benefit that if in the test file campaign you have done that, the benefit is that that correlation between the static and the dynamic pilot test is going to be helpful to you in case of working files, because in the working files you'll have a much better confidence that whatever is the value that you are getting from the dynamic pilot test, how it would have correlated had a static pilot test been done on those working files.
Farooq Ahmed has asked a good question, and that is, can we extract the soil spring values for HSDT?
Yes and no. I think it's it's both ways. One can calculate, one can determine those values, but as I initially said, there are a lot of things which are not without bias in case of dynamic pilot test. So I think I'll restrict my answer to the mathematical possibility, and mathematically, yes, you can extract the pile spring stiffnesses from the dynamic pilot test.
Kamran Javed has asked another question. How do you validate HSDT results with other testing methods? For example, low strain testing.
I think I already answered this in.
Yes, you have. Yes, just give briefly, you can say
So
briefly, running short of time.
The objective of low strain integrity testing, or SIT, is only to determine the integrity of the pile. Whereas the dynamic pilot test does two things. It does integrity and also the load carrying capacity. So the integrity part of both can be compared. And in fact, some of the defects which were not visible by the low strain integrity testing because of the small size of the hammer are now going to be more visible because of the large size of the hammer.
Amar Yasser, you have made a request. Dr. Sabi has made a request. I have a request to elaborate HSDT real-time video recording of HSDT along with results will be more fruitful in understanding HSDT. Now, Amar Saab, here we don't have so much of time. So you can contact Dr. Saab privately, and maybe he will be able to give you some video recordings, or he can, if possible, he can show you. Or you can contact our coordinator, Ms. Sadia Naveed, in this regard, to coordinate with Dr. Saab. So Nabil Ahmed has said, thank you for such a detailed and informative presentation. Yes, thank you very much, Nabil. I appreciate your message and your text message. Amar Yasser has asked another question. Can we differentiate skin friction and end bearing load capacity in HSDT, or HSDT only gives us skin friction?
So I think, again, I explained it earlier. We can differentiate. So you see, if you know the total capacity of the pile, and if you know the skin friction, then obviously it's quite easy to just subtract these two and determine the tip resistance as well. And this is exactly what is done in case of HSDT. So we can separate these two out, and we can determine separately by HSDT.
Dr. Saab, thank you very much. MashaAllah, a very enlightening lecture. You have thrown so much light on the subject which you were talking about. So I really thank you, and you have summarized the things in such an easy language and so comprehensively. So thank you very much. It was something which was in my mind, that when all the questions finished, I would ask you a last question. It is not a technical question, your personal opinion. What you have, all this technique, sonic testing and other testing techniques. Tell me personally what you feel, how much reliable they are in percentage, 50%, 30%, 40%, or still it is in a development stage.
Taisab, you put me on the spot, actually. So in my opinion, as I wrote there as well, there are two aspects to it. One aspect is the integrity part. I think it depends significantly on the person who is interpreting the results. And I would take that liberty to share that as well, that even the cross-hole sonic logging profiles that I was showing, you can just, the person who is interpreting, if he does not have a good idea of what is the right filter to apply, what is the right amplification and smoothing to apply, he can mess up everything. Major defects can be hidden by just playing with the data, and otherwise can also be done. So that's what make it very, very tricky. But if done properly, if the person, if people have experience and they have a good understanding of geotechnical engineering and their forward application, then I think these techniques are reliable. For example, the parallel seismic testing that I mentioned, if you just see that its ASTM standard was released in 2021. And it would be interesting for you guys to know that that is the first ASTM standard for that technique. And if you look at the research that was done on that, it probably started 15 years ago. So from 15 years ago, they were developing that technique. They were gathering enough data from around the world, from different case studies, to finally come up with an ASTM standard. So in 2021, they finally published the first ASTM standard for parallel seismic testing. So the point is, I think a lot depends upon the judgment of the people and their experience. But generally speaking, if we keep that factor out, I think they're fairly reliable.
Okay, thank you very much, Dr. Saab. And again, thank you for such an informative lecture. You gave so much deep insight on the topic you were speaking. Thank you again. And I would just request you to unshare your screen, please, so that I can see. I can't see Dr. Irshad among the audience. I just want to make sure that he's not there, if he's there or not there. I just wanted to give him a little time to speak. So I don't think he is here. He has left already, I think. Yeah, I can't see him. Okay, thank you. So we.
Before we leave, just a quick note. I can see Ziauddin Mia Saab, and to be honest, it's a great honor for me to have you, sir, here. And thank you very much, everyone, and thank you for the questions as well. Thank you.
Dr. Saab, apna Ziauddin Sahab is not only among the, you could say, in the audience, he's also the chairman of Pakistan Society of Civil Engineers. And this is why whenever he's there, we are really honored with his presence. And may Allah give him better health, and he lives long, and he remains over our supervision always. Thank you very much. So now just a few announcements. Ladies and gentlemen, the next lecture this month, we have two lectures, in fact. So the next lecture is on 26th October. Its topic is Impacts of Transportation on Climate Change. And our guest speaker would be Dr. Iza Anwar. I repeat, we have two lectures in this month. Now, the second lecture is on 26th October 2024, and the topic is Impact of Transportation on Climate Change. Speaker, Dr. Iza Anwar. For today's lecture, the certificates can be collected from 17th October, that is Thursday onwards, from 14A1 Block P, Model Town Extension, Lahore. And before coming, if you want to get a confirmation about your certificate, that is the person to contact is Ahmad Akram, and his cell number is 0347 462 5111. I repeat, the person to contact is Ahmad Akram, and his cell number is 0347 462 5111. And before I conclude, I thank you again, and I encourage everyone who has not yet become an associate of our society to consider joining it. It's simple to become the associate. Just go on the website. The procedure is described there, and it's very easy. And the annual fee is also minimal. It won't hurt you. And by joining PSC, you will also have the opportunity to contribute to the civil engineering profession through our various committees, where you can actively serve and support our shared goals. So this was what we had to share with you today. So now, before I close, I always I forget. I will just thank my team, Sadia and Hasnan, who worked behind the scenes to make this transmission more and more better and smooth. Thank you very much. I will see you on 26th October, inshallah. May Allah bless you all. Khuda Hafiz, Mia Saab, thank you very much.
Thank you very much, everyone.